Hello. Hello, everyone. I'm Sepideh Maleki, and today I want to talk about higher order and tuple-based massively parallel prefix-sums. I work on this with Annie Young and Dr. Martin Bircher from Texas State University. So prefix-sums are very important parallel primitives, and they have many applications. Just to name one that everyone knows, we can compute quicksort in parallel using prefix-sum. And so what is prefix-sum? So prefix-sum of an array is another array that every element in that array is the sum of all its previous elements. For example, here the prefix-sum of index 1 is the sum of 3 and 2, which result in 5. Another example is the index 3. The prefix-sum of 3 is the 2 plus 3 and plus 7, which result in 12. So as you can see, every element depends on the previous element in the prefix-sum. We can actually replace this sum operator with any other associative binary operator, and we can, and that way, generalize prefix-sum into prefix-scan. So these are some operators that we can use instead of addition, like min, max. And in fact, today I'm going to talk about two other generalization of prefix-sum, higher order and tuple-based, and later I'm going to explain what those are. Okay, so prefix-sum are fundamental building block of parallel algorithm, and we can compute them efficiently in parallel, and that is really important because there are many other algorithms that work like prefix-sum. That means every element depends on the previous element, and we can actually map those elements into prefix-sum and compute them in parallel as well. So some of these algorithms are radix sort, quicksort, buffer allocation, string comparison, lexical analysis, and many others, including data compression. Actually, data compression is what motivated us for this work. So today, basically, I'm going to explain, introduce a new algorithm called SAM that not only support the conventional prefix-sum, but it also supports two other generalization of prefix-sum named higher order and tuple-based, tuple-value prefix-sum. They are communicational optimal, and they need only a constant amount of work per thread, and I will explain later why this is important. And the carry propagation that we're using in this algorithm only needs a constant amount of auxiliary array and storage. And although it contains 3 algorithms, but it only has a 100 statement in CUDA. And to give you some results, we outperform COP, which is an NVIDIA library, and is actually the fastest library for prefix-sum by up to 2.9 on higher order and 2.6 on tuple-based prefix-sum. Since data compression is what motivated us for this work, I'm going to talk about it in this slide. So data compression basically contains of data model and decoder. The data model predicts the next value in the input sequence, and the decoder compresses that value. So one of the well-known delta model is delta encoding. Delta encoding computes the difference sequence in an array. The difference sequence is the difference between every 2 consecutive values in an array. And it has many applications. It's been used in data compression, in image compression, speech recognition, and compression, and many other algorithms. So delta encoding is embarrassingly parallel, but the problem is that delta decoding is not, and it actually appears to be sequential because every element, if we want to decode a current element, we need the previous element. And so that seems to be not a good fit for GPUs. But here I'm going to show you how we can actually make it to be a good fit for GPUs. So if you look at this example, if this is our input sequence, if we run the delta encoding on it, which is a different sequence, we'll end up having this input, and every element in this input is a difference between every 2 consecutive values here. And it turns out that if actually we run the prefix-sum on this difference sequence, we will get our input back. So that means the prefix-sum can actually decode these encoding values. And so we can since we can compute prefix-sum efficiently in parallel, that means we can compute the delta encoding, delta decoding in parallel efficiently as well. So what we just saw is the different sequence that we just saw is the first order. We call it the first order. The second order is, so the first order is the function of the current value and its previous value. And the second order is the function of the 2 previous value. And the third order is the function of the 3 value, and so on. So it turns out if we compute this higher order instead of the first order, we'll get the better prediction. So it's important to compute this higher order as well. And another thing is that the data that we want to compress usually appears in tuples. That means we might have x's and y's and z's. And it's important when we are running the difference sequence or the third order, we need to compute the difference sequence between all the x's. We don't want to compute the difference sequence between x and y. So that's important to compute, to work on each tuple separately. So the problem here is that this the conventional prefix sum that we have is not good enough to compute this higher order and the tuple-based values that we just saw. And all these libraries that they support Prefix-Sum, they are not sufficient enough to work on this higher order and tuple-based. So our solution for this problem is SAM. SAM is not only contains and support the conventional Prefix-Sum, but it also can support the higher order and tuple-based Prefix-Sum as well. And it can do it efficiently. So let's start with the sequential Prefix-Sum. So the sequential Prefix-Sum is a very trivial algorithm. As you can see, it has only a for loop. It has 2n data movement, and the complexity of this algorithm is only O of n. And that actually makes it really difficult for us, because if we want to have an efficient parallel Prefix-Sum, we have to do O of n work. That means that we have to have O of n application of some operator. So here is a scheme that shows how some libraries parallelize the Prefix-Sum, and it's been widely used, and many libraries use this scheme. So to begin with, we have this input array. We divide this into multiple chunks. So in the first phase, every chunk run a Prefix-Sum locally, and so we have the result of Prefix-Sum of each chunk here, and then we have to save the result back to the main memory. In the second phase, we will run the we will get the very last element of this chunk. We'll put it in the auxiliary array, and then we will run the Prefix-Sum on this auxiliary array. And then in the third phase, we have to get this. We have to reload the result and this result, and then add all this element to this corresponding chunk. And then we'll write the result back to the main memory. So we are reading and writing data in this first phase and last phase. So that implementation has 3 phases, and we are reading and writing data twice. So we have 4 main memory references. The auxiliary array needs to be stored in the global memory because the computation is between blocks. And so many high-performance libraries, they have multiple value per thread. That gives us a better performance. And Throughputs and CDPP are one of those libraries that are using this algorithm. So now let's see how SAM compute the Prefix-Sum. So SAM, in the interblock prefix level, it will compute the Prefix-Sum of each chunk, and then write the local sum of each chunk to an auxiliary array, and then write a ready flag to a second auxiliary array that shows that it's done with this local sum. And then in the interblock level, we'll read all the local sum of the previous chunk and we will add up the local sum to compute the carry, and then we use that carry to update the value, and then finally write the final result back to the global memory. So here I will explain that in more detail. So GPUs, for those people who are not really familiar with GPUs, they have multiple SMs, and each SM has multiple cores that have threads. So blocks is what organizes into these threads, and so we have multiple blocks here. So let's look at the block 3. So block 3 is running chunk 3 and chunk 7. So chunk 3 needs to compute the sum 3 first, and so all the data that it needs to compute the sum 3 it has it from the get-go. So we don't have any data dependency in this level. So once we're done with that, we'll write the result in the local sum array and then write a ready flag in this second auxiliary array. And then we have to compute the carry. So in order to compute the carry, let's look at chunk 7. So in order to compute the carry 7, we have to have the carry 6 and sum 3. So guess what? We already computed the carry 7, the carry 3 and sum 3. So we don't need to compute that anymore. And that's actually why our algorithm is fast, because we already have these red values here, and like we have it in every chunk that they already have been computed. So that makes our algorithm fast. And we only need to add these blue values here. And as you can see, there's a constant amount of them in every chunk. And we actually here, we only need to go back to this 3 value here to get these blue values. That's why we can actually use a constant amount of auxiliary array to compute this local sum. So we are using persistent block in this work, and this the same block process every k chunk. The carry only requires of 1 computation per chunk because of those constant amount of values that we have per chunk. And because of those blue values that we just saw, we can have, we only need the 3k elements at point of some time, k elements to write the, that we are working right now, k elements that we are removing, and k elements that are the safe values. And the local sum and the ready flag requires only constant amount of storage. And what we do here is that we have a write followed by independent read pattern. And we also computed our algorithm in the way that every block has to wait for the previous block to get the carry. And it shows that our approach is have a better performance. And actually, we are doing redundant computation for latency hiding. We also have multiple value per thread, and that actually makes our chunks bigger, but we can have a fewer chunks. So that's another point that will make our implementation fast. Okay, so we just saw how conventional prefix-sum works in SAM. Now let's look at the higher order prefix-sum. So we saw the first order, and that is the difference sequence. And we saw that as we go to a higher order, we will get a better prediction. So it turns out that the higher order, like for example, the second order is that the first order, and if we run the first order another time, we'll get the second order. And if we run it another time, we'll get the third order. So this is how we can get to a higher order. And since we can decode the first order with the prefix-sum, so if we run the prefix-sum multiple times, we can decode the higher order prefix-sum as well. So actually, this is how other libraries are working, are computing higher order. They have to iterate over the prefix-sum multiple times, and that's a good solution, but the problem is that it's not efficient, because then the memory accesses will be proportional to the order. Okay, so now let's see how SAM does this. So SAM does it very efficiently. We don't need to iterate the whole algorithm over and over again. We can only iterate internally, and that's why we can have, we don't need to read and write data in each iteration, and still we can have 2 memory references, and that's why our algorithm is efficient. The difference between the conventional prefix-sum and the higher order prefix-sum is that in the higher order, we have to have a non-Boolean flag array that shows that which order we are working on. And that's the only difference we have. And also, we have to have iterate internally. Okay, so now let's see how tuple-based prefix-sum works. So in tuple-based, we saw that the data might appear in X's and Y's. So the way we can actually, libraries can work on tuple-based in the following 2 ways. They can use reordering. That means that they can have X's for example, here X is in the beginning of the array and Y is in the end, and then run the prefix-sum separately and then reorder it again. So the problem here is that the reordering is not very efficient. So that will not give us a good solution. So another thing that we can do here, and some libraries like COP can do, is that they can define a data type and a plus operator, and then they can use that for tuple-based. But the problem is that this only works if the tuple sizes are small. And if we have a large tuple sizes, that will not work very well because we will eventually run out of register. Okay, so now let's see how SAM does this. So SAM again works with tuple-based very efficiently. We don't need any reordering. We don't need to define any special data type, and because of that, we can have the same amount of data per thread no matter what. And the only difference here is that we have to have a multiple sum array, each per tuple, and but still we can have the constant amount of auxiliary array and the flag array. We don't need to change anything to the flag array. Okay, so we compared our algorithm with these other three algorithms, Trust, CDUPP, and COP. So as you can see, COP and SAM have 2n memory references, whereas CDUPP and Trust have 4n. We run our code on Titanex and K40 NVIDIA GPUs, and Titanex is the newer GPU, and K40 is the older one. Okay, now let's see some results. So first, let's see the conventional prefix-sum result. So we have the throughput here in billions of items per second, and the input sizes here. We have both powers of 2 and powers of 10 to show that our algorithm works well on both powers of 2 and powers of 10, and non-powers of 2. And so as you can see, SAM and COP are doing better than CDUPP and Trust, and that's actually the power of 2n versus 4n. But COP is doing better than SAM on actually most of the problem sizes, except the very last two which are the largest one. And we have the same result for the 64-bit integers as well. And what we did also is that we computed the CUDA-MEM copy throughput, and we saw that for the very large problem sizes, the throughput of SAM is same as the CUDA-MEM copy. That means that you cannot have a better algorithm for this GPU than SAM, because CUDA-MEM copy doesn't do any computation. So SAM is optimized for this GPU. So here is the result for K40. So on K40, we are still doing better than CDUPP and Trust, but COP is doing better than SAM by about 50%. And same result for 64-bit integers as well, except COP is, the difference between COP and SAM is smaller here. And one of the reasons is that so SAM has only one code for all the architecture, whereas other libraries like COP here, they optimize their code. They have actually basically different codes for different GPUs. And now let's look at the higher order throughputs. So let's start with Titanex. We only compare our code with COP, since COP was doing better than all the other implementation of Prefix-Sum. So on order 2, we are doing better than COP by 50%. On order 5, we're doing better than COP on 78, and on order 8, we're doing better than COP by 87%. That means that our SAM's performance advantages increases with higher order. The reason is that COP is iterating over the order, and that makes the more accesses to the global memory. And that's why as we go to a higher order, the performance of COP will be worse and worse. And we have the same result for 60-bit integers as well. And let's look at the K40 result. So since COP was doing better than SAM on the K40, so here is COP is doing better than SAM on order 2 and order 5, but we kind of tie on order 8. But still, our SAM's performance increases with the higher order, and In fact, if we have the higher order like 9 and 10, SAM would do better than COP. We have the same result for 60-bit integers as well. The difference is that here since we did better in 64-bit integers on K40, we are doing better than COP on order 5. Okay, now let's look at the results on Tuple-Based. So on Tuple-Based, COP is doing better on 2 tuple sizes, but then as we go to larger tuple sizes, because in COP will run out of register, we will do better than COP. And as you can see, we are doing better than COP, and SAM is doing better than COP on 5 and 8. We have the same result on 64-bit integers as well. And the important here is that the performance advantages of SAM increases with the larger tuple sizes. We have the same result for K40, but still K40 did not give us a good performance for SAM in conventional Prefix-Sum. So here, as you can see, COP is doing better than SAM on 2 and 5, but then we are doing better on 8 tuple sizes, and we have the same for 60-bit integers as well. Okay, so to sum up, we just saw a new algorithm for prefix scan, and that also support higher order and tuple-based. We saw SAM's performance on Maxwell and Kepler GPUs, and SAM reaches the CUDA memcopy throughput on very large problem sizes, and it outperforms all alternative by up to 2.9 on higher order and 2.6 on the 8 tuple sizes Prefix-Sum. And the important thing here is that the relative performance of SAM will increases with higher order and larger tuple sizes. You can download the code here, and thank you if you have any questions.
Okay, if you do have questions, please come to the microphone, state your name and affiliation, if there are any questions.
Aaron Su, Indiana University. One thing I like is that you've got a 100-statement CUDA kernel for scan. I think that's should not be overlooked. But you mentioned your tuple sizes. Do you have a limitation on the size of your tuples? And if so, or if not, what are the sort of trade-offs with increasing your tuple sizes in terms of memory or performance? Is there a hard limit you can't go over, reasonably speaking?
Right. So right now it only supports up to 32, but we are changing the code so it can support larger. The reason is that the warp-ist only has 32, and that's why right now this code can only support up to 32 tuple sizes.
Thanks.
Tyler Sorensen, Imperial College London. I saw in your slides that you had a flag array and sum array, and so you're doing fine-grained synchronization between these blocks, which means you need to think about the memory consistency model. Did you include fences in the application, and what is the reasoning you use to include the fences? Because CUDA doesn't have a fantastically well-documented memory model.
Right. So yes, after we compute the local sum, we have to use a fence and then write the ready flag, and that's the only place that we are using fences.